Okay, let's continue. So that was about regression, and now we're moving to a next subject. Is called support vector machine. So let's start our introduction. Unlike regression, for support vector machine is talking about a problem that is similar but different. It is talking about classification problem. Of course, it's a very important subject in machine learning. So intuitively, what's this? Is that we give you a set of data or a data set, okay? So you get again some independent variables and an outcome variable or dependent variables, okay? So to make the explanation and the derivation easier, I'm choosing a different notation, different from the regression part. So here, n is the number of variables you have, and m is the number of how should I say that, data points you have. Okay, you will see why I should use n to be the number of variables and m to be the number of data points, because that's going to give you a formulation that looks similar to your familiar nonlinear programs, linear programs, whatever. Okay, coming back to the formulation. So you get several properties or several features, and that may be helpful for you to do a determination about whether your yi should be 1 or -1. Here, 1 and -1 means success and failure, means boys or girls, means A or not A, means death or birth or whatever. So pretty much you are trying to do some kind of classification of each data points. So there are of course many examples or applications. For example, today there are a lot of applications talking about image recognition. Okay, so you are given a picture, and you get some kind of entities there. So for example, you get something like this. So I guess everybody knows what's this. This is a pig, all right? So how we know this is a pig? There are several different kinds of models, blah, blah, blah. But anyway, a classification problem is that whenever you get a photo, determine whether there is a pig there or there is no pig there, all right? So pretty much that's classification. And then you will get several features from this picture, like for example, all the RGB values for each pixel, whatever. Then those are features. So let's focus back to theory or the abstract formulation. So we want to find a classifier to assign data point I to a class, either pig or no pig, according to xi. Okay, we want to read this information and we will assign this data point to a class. And once we do this assignment, we get some kind of yi hat. We determine its class, and then we check whether we are doing right or wrong. We want to somehow minimize the total number of classification error. That's about classification in general. Okay, so general classification can be I shouldn't say it's difficult. It's having a lot of possibilities. So let's do simple. Let's do linear classification. Okay, so what do we mean by linear classification? Let's start with an example here. Suppose you only have two features of each data point, and here blue means 1, green means -1, or the other way, as far as you like. So now we are trying to do linear classification, means we should draw a straight line to separate blue dots and the green dots. Okay, so a straight line means something like this. Okay, or you may do something like this, something like that. So there are many different straight lines that may do the work. Okay, so this is a 2-variable example because it's easier to do visualization. Of course, in practice, you may have a plane in the 3-dimensional problem or a hyperplane in higher dimensional problems. We are just using a line to make the visualization easier. Okay, So as we mentioned, there are infinitely many lines that may do the separation. We somehow need to tell our computer, tell our model, one way to choose the best line. So we need to define best. How do we do that? Well, some people say, let's find the line that is the farthest from both group. Okay, so that means we want to find a line, for example, this one. Okay, once we have a line, then for each group, we may see what's the distance from each point to a line, from point to the line. And for each group, there will be a point that is closest to the line we try to propose. Then there is a distance. Okay? From another set, there is also a point that is the closest. So for all the points, there is a distance to the line, and we try to minimize, we want to maximize that distance, that minimum distance. Okay, so in that case, if we draw a line in this way, okay, as I printed here, then the distance is the length of this red line segment. How about this? I'm going to draw another line. If I draw the blue line, then you may see that for the minimum distance now is just the blue line segment, and that minimum distance is not as large as the red one. So this blue proposal is not very good. Or how about this? I'm going to draw another line like this one. Then again, even though this line is far from the blue one, but it's too close to the green one, so it's also not good. So that's the idea of choosing the separation hyperplane. Try to make it as far as from all those points. Okay? So once we agree to do that, technically we may define several terms. First, we get two dashed lines here. They are called supporting hyperplanes, one for each group. So you may check the definition for supporting hyperplanes. But anyway, given a set, a supporting hyperplane is a plane that separates all the set to one side of it and is the closest to that group. Okay, so I hope you agree that is indeed these dashed lines. And then the 2 points, x1 and x2, they are called support vectors. Okay, somehow they define the hyperplanes, the supporting hyperplanes. So the name support vector machine is a model, or you may say it's an algorithm, whatever. It's a model that tries to find the best separating hyperplane, which may be expressed in general in this way. Alpha plus beta transpose x equals 0, the typical formula for a linear function. Okay, so that's the idea. Later, let's see how to do the formulation.